In the heart of our solar system burns a colossal nuclear furnace, a seething, churning ball of superheated plasma that we call the Sun. For billions of years, it has faithfully provided the light and heat that make life on Earth possible. But our Sun is not the steady, unchanging beacon that it might appear to be from our comfortable vantage point 150 million kilometers away. It is, in fact, a dynamic, ever-changing star currently entering one of the most active phases of its 11-year cycle. And the implications for our planet could be profound. The Sun is surging with activity in ways we haven't seen for decades, and scientists around the world are watching with a mixture of fascination and concern. Not only did they predict this heightened activity, but they continue to observe incredible new solar phenomena that could affect everything from our power grids to our satellite communications, and even the spectacular light shows in our skies, all some 150 million kilometers away. The Sun isn't just a ball of fire. It's an intricate celestial body with layers, rhythms, and cycles. At its core, nuclear fusion converts hydrogen into helium at temperatures of 15 million degrees Celsius, releasing the energy that radiates outward through its various layers. The visible surface we see is called the photosphere, above which lies the chromosphere and the extended corona that stretches millions of kilometers into space. But what concerns us most right now is what's happening on the photosphere, specifically the dark blemishes known as sunspots. When I look back at historical data, I realize how little we actually knew about the Sun's cyclical behavior before modern observations, says solar physicist Dr. Valentina Zharkova. We're discovering things we didn't know were there to be. Discovered, time after time. So, are you curious to see what they've learned? I'm Alex McColgan, and you're watching Astrum. In today's video, we'll explore everything you might want to know about the current solar maximum, from the science behind solar cycles to the potential impacts on our technology and the spectacular phenomena it could create in our skies. It's one of life's little ironies that the star we see every day remains one of the most mysterious objects in our cosmic neighborhood. The Sun's magnetic field, the engine driving all this activity, is generated by a churning ocean of charged plasma within its interior. This dynamo creates a magnetic field that becomes increasingly twisted and complex over the 11-year solar cycle. Eventually, this twisting causes the magnetic field to snap and reconnect, releasing enormous amounts of energy in the form of solar flares and coronal mass ejections, CMEs. These solar flares are categorized much like hurricanes, with classifications, ranging from the relatively common C-class flares to the more powerful M-class to the enormous X-class flares that can release energy equivalent to billions of hydrogen bombs. The largest flare ever recorded was an X-28+ in 2003, but even that pales in comparison to the legendary Carrington event of 1859. A solar storm so powerful that telegraph systems worldwide failed, and auroras were visible as far south as the Caribbean. Of course, in 1859, we didn't have power grids, satellites, or the internet. Today, a Carrington-level event could cause worldwide blackouts, disable satellites, and disrupt global communications for weeks or even months. Such is the conundrum of modern civilization, where technological advancement has inadvertently made us more vulnerable to the violent moods of our parent star. Let's start with one of the most consequential aspects of increased solar activity: sunspots. These temporary dark patches on the Sun's surface are areas where intense magnetic fields emerge from below the photosphere, inhibiting heat transfer from the Sun's interior. Despite appearing dark, they're actually blazing hot, around 4,000 degrees Celsius, though cooler than the surrounding surface at 5,500 degrees. Sunspots are the visible manifestations of the Sun's internal magnetic dynamo. Their number, fluctuates over the approximately 11-year solar cycle, rising to a peak known as the solar maximum before declining to a solar minimum. The current solar cycle, cycle 25, began in December 2019 and was initially predicted to be relatively weak. However, it's defying expectations. By early 2024, sunspot counts were already exceeding predictions, with some days showing over 200 individual spots, numbers we haven't seen since the extremely active cycles of the 1950s. Each of these sunspots is a potential launching pad for solar flares and coronal mass ejections. When the magnetic field lines above a sunspot group become too twisted and stressed, they can suddenly reconnect in a process called magnetic reconnection. This releases an enormous amount of energy in just minutes, up to 10^25 joules in the largest flares. That's equivalent to the energy from 10 billion Hiroshima-sized atomic bombs released in a matter of minutes. The flares themselves are just the beginning. The most impactful solar events occur when a coronal mass ejection, billions of tons of charged particles, is hurled into space at speeds up to 3,000 kilometers per second. If Earth happens to be in the path of this plasma cloud, the results can be spectacular or catastrophic, depending on your perspective. Backups, and good backups at that, have become key to protecting our modern infrastructure from these solar storms. Power grid operators have installed systems that can disconnect transformers before they become overloaded by geomagnetically induced currents. Satellite operators can put their spacecraft into safe modes during serious solar events. And space. Agencies monitor the sun 24/7 using spacecraft like the Solar Dynamics Observatory, SOHO, and Parker Solar Probe, providing early warnings when dangerous eruptions occur. The Parker Solar Probe, launched in 2018, deserves special mention. It has ventured closer to the sun than any human-made object in history, flying through the outer corona multiple times to directly sample the solar wind. With a custom-built heat shield that can withstand temperatures of 1,170 degrees Celsius, it's providing unprecedented data about the mechanisms that heat the corona and accelerate the solar wind. The discoveries we've made challenge our understanding of how stars work, says Nicola Fox, director of NASA's Heliophysics Division. Parker is rewriting the textbooks on solar physics. Another key to understanding the current solar activity lies in its magnetic field. The sun doesn't rotate as a solid body. Its equator spins faster than its poles. This differential rotation stretches and twists the magnetic field lines, causing them to become increasingly complex and unstable over the course of the solar cycle. When a critical point is reached, the field essentially resets itself, flipping its north and south. Magnetic poles. This magnetic reversal marks the peak of the solar cycle, the solar maximum, where we find ourselves today. The impacts of this solar maximum extend far beyond the sun itself. When charged particles from CMEs reach Earth, they interact with our planet's magnetosphere. This interaction can compress our magnetic shield on the day side and stretch it into a long tail on the night side. As these particles funnel down into our upper atmosphere along magnetic field lines, they collide with atmospheric gases, causing them to glow, creating the breathtaking phenomenon we know as the aurora borealis and aurora australis. Each Voyager spacecraft, those incredible machines that have taught us so much about our solar system and now travel through interstellar space, has a 3.7-meter antenna that was once pointed back toward Earth. Those same antennas that transmitted spectacular images of our outer planets now tell a different story, of increasing cosmic ray intensity as the probes exit the protective bubble of the sun's heliosphere. This connection reminds us that the sun's influence stretches far beyond Earth, creating a protective bubble around our entire solar system. Durability is a chief concern during intense solar activity. There are many unknowns when the sun becomes this active. GPS accuracy can degrade. Communication blackouts can occur, especially in polar regions where airline routes are affected. Astronauts aboard the International Space Station may need to shelter in more heavily shielded modules during intense radiation events. And perhaps most concerning, power grids, especially those at higher latitudes, can experience surges that damage transformers, potentially causing widespread blackouts. Even with all these challenges, and with our technological systems performing better than engineers could possibly have hoped for, given the current conditions, there's still at least one more hurdle to cross. The peak of this solar cycle isn't expected until 2025, and some solar cycles feature multiple peaks. We may not have seen the worst, or the best, depending on your perspective, of what this solar maximum has to offer. But, with all this activity, what can we expect to see? For most people, the most visible effect will be expanded auroral displays. During moderate solar storms, the northern lights become visible much further south than usual, while southern auroras push northward from Antarctica. During the most intense events, people as far south as Florida and as far north as New Zealand might glimpse these ethereal light shows that are normally reserved for polar regions. The current surge in solar activity already triggered several spectacular auroral events in 2024, with curtains of green, red, and purple light dancing across skies in places unaccustomed to such displays. Social media feeds filled with images of auroras captured from unexpected locations, testament to both the strength of the solar activity and our increasing ability to document these fleeting phenomena. 13 days after the last major X-class flare, the Earth experienced a geomagnetic storm that lit up the skies across Europe and North America. It might remind you of the Halloween storms of 2003, when similar widespread auroras were visible. I don't know about you, but I find these displays so hauntingly beautiful, especially knowing the cosmic violence that creates them. But we've got a long way to go before this solar cycle subsides. So let's move on to what researchers are learning from all this activity. It would be almost 2 years before we expect the sun to return to a quieter state. Not bad, considering it's been ramping up since 2019. Scientists are taking advantage of this active period to gather unprecedented data, hoping to answer fundamental questions about solar physics. Why is the sun's corona hundreds of times hotter than its surface? What exactly triggers solar flares? And how can we better predict dangerous space weather events? Now, this current solar cycle was not originally predicted to be particularly strong. That honor was supposed to go to the previous cycle. However, contrary to expectations, Cycle 25 is shaping up to be one of the more active cycles in recent memory. This underscores how much we still have to learn about predicting solar behavior. The sun, it seems, still has many secrets to reveal. When we think about climate, we think Earth, but the sun also has its own form of climate. Thanks to ancient tree ring data, ice cores, and historical sunspot observations, scientists have long suspected that extended periods of minimal solar activity, like the Maunder minimum of 1645–1715, coincided with cooler periods on Earth. What's fascinating is that the current high activity doesn't necessarily translate to significant warming, as the variation in total solar irradiance is actually quite small, just 0.1% between solar minimum and maximum. Before we leave the topic of space weather impacts, I did promise we would come back to technology. Possibly the biggest shock from increased solar activity comes from its effect on our satellites. Low Earth orbit has become increasingly crowded, with thousands of satellites providing essential services. These spacecraft are vulnerable to several solar effects, from increased atmospheric drag during solar storms to direct damage from radiation. This photo shows what happens when a charged particle from a solar event hits a camera sensor on a spacecraft. That bright spot is actually damage to the equipment. It would have been incredible to capture this kind of image when technology was less advanced. Imagine the panic it might have caused in mission control. Together, this dynamic duo of increased solar flares and CMEs is set to take a dazzling parade of pictures that will revolutionize our understanding of solar physics. But don't take my word for it. Let's jump in and see what some recent images from solar observatories show us. Something that immediately stunned scientists was the complex structure of recent coronal mass ejections. They expected to see straightforward ejections of plasma, but what caught them by surprise was the intricate rope-like magnetic structures visible in high-resolution images. You can immediately see how dynamic the corona becomes during these eruptions. When the sun's activity reaches toward Earth, it interacts with our magnetosphere in complex ways. The pressure exerted by solar wind compresses our magnetic field on the day side, while stretching it into a long tail on the night side. When a CME hits, it can temporarily deform this magnetic bubble, allowing particles to enter along field lines at the poles, creating those spectacular auroras. But magnetospheres aren't unique to Earth. Every planet with a magnetic field has one. Jupiter's magnetosphere is the largest structure in the solar system next to the heliosphere itself. If we could see it from Earth, it would appear larger than the full moon in our sky, despite being hundreds of millions of kilometers away. In early May 2024, Earth experienced one of the most intense geomagnetic storms of the current solar cycle. Imagine you are sitting at home when the sky outside suddenly begins to glow with shimmering curtains of green and purple light. You might think your eyes are playing tricks on you, especially if you live far from polar regions. But this isn't an illusion. It's the visible manifestation of our star's increasing fury. It turns out that in times of extreme solar activity, these auroras can appear almost anywhere on Earth. During the Carrington event, people in Cuba reported seeing the night sky filled with red light so bright they thought nearby cities were on fire. We've not reached that level in our current cycle, but the possibility remains as we approach solar maximum. After all, the probes are already starting to fail. Not the solar observatories, they're working perfectly, but our aging fleet of space weather monitors is increasingly being strained by the demands of constant observation during this active period. While NASA and other space agencies are developing new spacecraft to study the Sun, we rely heavily on instruments that have far exceeded their design lifetimes. For now, though, we continue to learn from each eruption, each flare, each geomagnetic storm. This solar maximum is a perfect natural laboratory for understanding the complex dance between our star and our planet. And while it poses challenges, it also offers opportunities for scientific discovery, for technological advancement, and for simply appreciating the raw beauty of nature operating on a truly cosmic scale. Thanks for watching. I was honestly blown away by all the incredibly kind comments and messages you've sent me about previous solar videos. Everyone here at the Space Truths team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Space Truths content about our Sun. I'll see you next time.